We're going to be looking at LEDs, and we're going to be trying to see how PN junctions can be used to create light emitting diodes and emit light. So let's start with what we know, which is your average PN junction. We have our P-type, and we have our N-type. And when we draw the band diagram for this, we see that there is, on the P side, there's an excess of holes, and on the N side, there's an excess of electrons. And then in the middle, because those electrons and those holes recombine at the junction, there's there's a lack of holes and electrons, which is why we call it the depletion zone. And so this is the band diagram laid out. And where these holes and these electrons recombine in the center, which also creates these ionized acceptors and donors at the junction. Now, the way that we can use the characteristics of a PN junction to create light is if we use a semiconductor that's specifically a direct band gap. Why that's important? So we're going to look at the noodle plot. To explain how that works, we're going to look at the noodle plot for our PN junction band diagram. If you're not familiar with what these are, basically this line that we draw for the band is the minimum energy, is the minimum conduction energy in the maximum valence energy state that these electrons and holes can occupy respectively. But in reality, there's a whole array, there's a whole set of energy states that they can occupy. We just are only concerned with the very edge of it. And so in looking at an energy diagram like this, you can see that in this example, which is an indirect semiconductor, this is mapping location X. So you can see this is an indirect semiconductor where the minimum conduction energy and the maximum valence energy don't line up. And as a result, when you, for example, recombine an electron with a hole, like here, you end up using extra energy in the form of heat to be able to get it to the right X location, as well as dropping down. And so as a result, none of the energy goes into generating a photon. Part of it goes into generating what's called a phonon, which is what is the particle that causes the heat. Now, if we had a direct semiconductor, you don't waste any of that energy when you recombine as heat. Instead, it goes directly into forming a photon, and this is something called spontaneous emission. That photon has now an energy which is equal to the band gap. And you can calculate what the wavelength of it is by using the conversion 1240 divided by E sub g is equal to wavelength, lambda. Now, what that means for this is that if we have a direct semiconductor, then when these holes and these electrons recombine in the center, it emits a photon, right? Now, of course, there's not going to be an infinite number of electrons and holes to allow for recombination. So what we do is we just supply a forward bias. And this replenishes the number of holes on the P side and the number of electrons on the N side, allowing for continuous spontaneous emission. Now, we're going to look at the IV plot for one of these LEDs to understand a little more their characteristics. So an LED is just a diode, a PN junction, so we can use the same equations that we use to characterize the IV plots of PN junctions to be able to characterize the IV plots of the IV plots of an LED. So we know that I is equal to I naught, the exponential of QV divided by KT. And then we know that I naught is proportional to the intrinsic carrier concentration squared, which is equal, or I guess is proportional to the exponential of minus E sub G over KT. And so we can describe the current as this function, the exponential of QV minus E sub G over KT. And why this is cool is it shows us how the color of the LED is related to the current with which it emits, because as we talked about a couple minutes ago, the wavelength is related to E sub G, and so when you have a larger band gap, you have both a smaller wavelength of light, which is what causes these. When you have a larger band gap, you have a smaller wavelength of light, which is what causes these lights to form. But then you also have, if you have a larger band gap, you have a smaller term up in the exponential, which causes it to be less steep, the IV plot. Whereas if you have a really small band gap, then this term is larger, which creates a larger slope. And so this is how the IV characteristics of a LED behave. And so the next thing I want to look at, in addition, is band gap engineering, which is basically, like, as we mentioned, we need these direct band gap semiconductors to be able to create LEDs. But then we also need to make sure that the substrate we put them on has lattice matching. That is, it has the same lattice constant, so that you can actually build these LEDs on a substrate. So to design an LED, we need to have both a substrate, and then we need to put whatever material it is that we're going to dope PNN on top that has the band gap energy we need, or the wavelength, produces the wavelength of light that we need, while at a lattice constant that matches the substrate, because we need lattice matching. And so to kind of explain how one does this, we're going to walk through a problem which helps to conceptualize this. So let's walk through a problem that kind of walks through how this works. You are fabricating red, green, and blue LEDs from binary compounds or ternary group 3, group 5 semiconductor alloys given in the chart below. Calculate the composition of the semiconductors that you need for a red color LED along with a suitable substrate. Explain the choice of composition and substrate. Okay. So first, we're going to, we want to make a red LED, which occupies a band gap energy somewhere along here, 700 nanometers, a little less than 2 electron volts. And we need it to be composed, and we need to make sure that it's a direct semiconductor, because you can see these dotted lines represent indirect semiconductors. So what looks most obvious to me would be something like using germanium as a substrate, because it matches the lattice constant here, and then using some kind of alloy of GaPas. So following something along this line. Or, sorry, I misread. GAALAS. Now, to what amount, we can kind of just, it's a little bit of guessing with like a diagram like this, but it'd be something like, okay, maybe 70% gallium and like 30% aluminum, since it's closer to the gallium than the aluminum. So we can write that out as GA 0.7, aluminum 0.3, and arsenic. And then for choice of substrate, we pick germanium. And the reason for this, again, is because we need something that's a direct band gap, but that also exists at the energy that we need, and then also exists, also has another substrate which can match the same lattice as it. And so in this scenario, that's the only one that can really work. Similarly here, we need to manufacture some kind of we need to find a semiconductor whose band gap can work for blue and green. So I suspect something like this, where we use some combination of indium, aluminum, and nitrogen for the semiconductor part, and for the substrate, some combination of gallium, indium, and nitrogen, which will have a lattice that matches it. And in this case, for the question, is it possible to choose one substrate to fabricate all LEDs, red, green, blue? Why or why not? We can say no, because we notice that there is no alloy that functions throughout this entire wave, right? There's parts that occupy this space, parts that occupy this space, but nothing that occupies the entire visible spectrum. And so as a result, there's no one semiconductor that can do it all. Now, the last thing we want to talk about is how can we create white light, right? Because that's something that's very important when designing LEDs. And there's two main ways of doing it. One is just to combine three lights. So the most common thing you can do is you can take RGB, red, green, blue, and you can combine them. And so in that case, we would take the blue LED, the green LED, and the red LED we just made, and we just put them together, and it would form an emission spectra, which is an emission spectra, which basically describes the intensity of each of the different lights. So since red exists at around 700 nanometers, and green exists at around 630, and blue exists at around 400 or 500, we would imagine that the emission spectra for this looks something like this. The reason for these different intensities is because generally when you create LEDs that are red light versus green and blue light, you see like variations in intensity like this. And so this is one way of doing it, just combining R plus G plus B. But more modern way of doing it that creates a better light is using a UV LED, right? So an LED that's in the ultraviolet, and then using a phosphor layer. And this creates a way more smoother spectrum, because we have our UV LED, and then when this UV light hits the phosphorus, or the RGB phosphor, it creates a much smoother band diagram. As you can see, you don't have all this variation. You have more constant. And yeah, that's kind of covering pretty much everything regarding LEDs. The main aspects to note are how p-n junctions are used to create LEDs, then what their IV characteristics look like, and then how we can do these kind of bandgap engineering, and then finally what the emission spectra looks like. And one more thing to note about the emission spectra, because this is spontaneous emission, which that means that every single LED is like moving in a different direction and it doesn't necessarily have the exact same wavelength. It doesn't behave exactly the same, each photon that gets released. And so as a result, when you look at the emission spectra for, say, for example, like the red LED we looked at, it's not very focused. It's a lot more smoother. Even this is, like, you'll see compared to lasers, for example, is a lot more smoother, whereas lasers look like this because they operate under stimulated emission rather than spontaneous emission. So that's the other key aspect, is to look at like the emission spectra for these LEDs and see how they behave. Thank you so much for watching. If you have any questions, please leave them in the comments. And if you like the video, feel free to like and subscribe.